Hello, thank you very much for the kind opportunity to give this short presentation. My work is joined with Matt Insall from Missouri S&T I at Rolla. This talk is devoted to the concept of a norm on a category. This concept has been studied extensively, going back to Lever in 1973. Well, there has been an entire industry developing from this concept, but our approach is a bit different. So let me explain how. So the main motivation is that we want to take a large class of morphisms. So when you take metric spaces, you normally consider as morphisms something like short maps, or also called contractions. So why are you doing that? You are doing that to achieve good categorical properties. But now, often you need more maps, sometimes even wild set theoretic maps. So our idea is to use an additional structure to be able to work with large classes of morphisms. And the second motivation is that we want to give a convenient framework to metrize equivalence classes of spaces in such categories. So again, in the case of metric spaces, there's the well-known Gromov-Hausdorff distance for compact metric spaces and various generalizations for the non-compact case. But when you do the metrizations, you often have to do arbitrary choices, and it's becoming technical, and we want to give a convenient framework for such metrizations. And finally, it turned out that an axiom in the setup will become a variation of the Cantor-Schroeder-Bernstein theorem. So now let me tell you what kind of axioms I want to impose. So first, I will call a semi-norm simply a map from the category to the non-negative real numbers, satisfying the obvious axioms. So the axiom that on the identity morphisms the norm should vanish, and secondly, that the triangle inequality should hold. And then now I will introduce a terminology. I will say that two objects x and y are norm isomorphic if they are maps in both directions inverse to each other with vanishing norm. So in other words, an isomorphism that is witnessed by maps or morphisms with vanishing norm. So now I can define a norm. A norm is a semi-norm such that if I have morphisms with vanishing norm in both directions, then x and y are actually norm isomorphic. So I can improve f and g to be inverse to each other. And the last axiom N4 says that if the assumption of the previous condition holds only up to epsilon, then it actually holds. So now note that condition N4 becomes empty as soon as the set of values of the norm is discrete. But now, to get a feeling for what I just said, it's very instructive to look at some examples, and before this I want to tell you the important principle. The important principle is that a norm, a semi-norm, becomes a norm as soon as you restrict to compact objects, where compact has to be understood in a suitable respective sense. So now the examples. So first, I will define a norm on sets. So this norm will simply count the number of pre-images of an element. And you will realize that a morphism or a map has vanishing norm if and only if it is injective. So this means that the condition of a norm boils down to saying that if I have injective maps in both directions, then both sets are in bijection to each other. But this is the well-known Cantor-Schroeder-Bernstein theorem. So let's put a bit more structure on the setup. Let's impose that we have graphs. Now it's an easy exercise to realize that the previous norm, the norm from sets, is not a norm, it's only a semi-norm, but you can rescue the day by restricting to finite graphs. And in a discrete setup, finite is the right thing for compactness. And now let's do a bit more analytic example. Let's take vectors, real normed vector spaces, and define this norm on a morphism, so on an operator that looks a bit topsy-turvy because it's like the operator norm turned upside down. But it still makes sense. Its vanishing norm says that the operator is expansive, and you can check that this semi-norm becomes a norm as soon as you restrict to Hilbert spaces. So now the last two examples are more involved and more interesting. So in the case of topological spaces, you can define a norm by counting the number of components of the pre-image of a component and adding to this the number of increase of dimension by forming the pre-image. Actually, both terms are semi-norms in their own right, but the sum becomes a norm, and this is nothing but the well-known monotone light factorization. And now lastly, there is the example of metric spaces. As I said above, I'm especially interested in the Gromov-Hausdorff distance. So in this case, the convenient semi-norm is the dilatation semi-norm that measures how much 2 points get closer to each other under the morphism F. And now it turns out that, again, by now restricting to compact spaces, actually you can recover the Gromov-Hausdorff distance, so the comparison map is 2 Lipschitz in one direction and Cauchy continuous in the other direction, meaning that Cauchy continuous sequences are preserved. And now let me give an outlook of what's going ahead. So something very important is that we want to prove theorems in the setup. So first, we want to prove the Freundal-Hoyevich theorem. That is just the theorem that allowed me to prove this comparison for Gromov-Hausdorff distance on the last slide, but we want to formulate it purely categorically. And secondly, we want to formulate the Kantorowicz-Rubinstein theorem in the setup. So the Kantorowicz-Rubinstein theorem characterizes the well-known Wasserstein distance. And the next big step ahead is to treat non-compact objects. So this is again motivated from metric spaces. So you take an object that you can describe as an inductive limit of compact objects, and then there's a convenient way to define a semi-norm. So the morphism in this int category is a limit of co-limits. So the idea is that you have an exhaustion of the object. So if this x is the object, you somehow have an exhaustion, and you will want to form an integral along something you should think of a probability measure. So think of this like integral with respect to a probability measure, but instead of a probability measure, you take a map from your index category to the 0-1 interval that you think of as a distribution function, and then you can define this integral first by defining the density function for the co-limit, and then for the limit becomes the integral. So thank you very much for your kind attention, and there's a preprint available.